All right, so next up is going to be the cardiac cycle. And during this discussion, we're going to fill in the rest of the information that we originally listed for number 2 and number 3. So for number 2, the cardiac cycle is composed of 4 phases. And we're going to talk about what those 4 phases are. And we're also going to talk about how we can measure those 4 phases with something called an EKG or an ECG. So electrocardiogram is what that stands for. And that's going to be where we have our PQRST model there, and we'll talk about that. And then we'll also mention how the pressure and volume relationship, what that looks like in the heart at any given time, and how we can measure that. And in order to talk about that, we also have to be wary of what's happening with the valves and when they're opening and closing. And so in order to measure what's going on with the valves as they're opening and closing, we can actually measure that with a stethoscope. We can hear that if we put that on the patients in specific areas. I actually have a picture of where you can do this and test this on one another if you're interested. So we'll talk about these 2 things next. All right, so first up, let's talk about what a cardiac cycle even is. So the cardiac cycle starts at one heartbeat, and it continues on until the beginning of the next heartbeat. And it's divided into 2 general phases, systole and diastole. And this might sound familiar to you because you might have taken a couple blood pressures and you know that the systolic number is on top of the diastolic number. And so what systole actually means is that's the contraction phase of what's going on in the heart. And then diastole is the relaxation phase. So whenever you're actually measuring that blood pressure, you're measuring the pressure of the amount of blood after an immediate contraction in the systolic number, and then what's the pressure of blood remaining during the relaxation phase, the diastolic number. So you would imagine that the systolic number should be larger than the diastolic number because after a contraction there should be more built up of pressure, and so that's usually why the systolic number is higher, or in a normal patient, I should say. And then just one quick note before we keep going into this. Remember that fluids also like to move in the direction of what we've talked about, like with ions and with gradients, temperature gradients, all different types of gradients in anatomy and physiology, where things like to move from a high to a low concentration. If things want to move in the opposite direction, then we have to usually input some sort of energy or transporter or something. But here we're not even going to talk about that. We're just bare bones. Things like to move from a from a high to a low concentration for pressure of fluids. Okay, so we can even further divide those 2 base portions of the cycle into 2 separate individual pieces. So there's 2 types of systoles and 2 types of diastoles, because we have to talk about what's happening at the atria and what's happening in the ventricles. So there's an atrial systole and an atrial diastole. So the atria are contracting and then the atria are also relaxing. Then we also have to talk about how when the ventricles are contracting and when the ventricles are relaxing. So if we wanted to manipulate and make like a computerized generated version of the cardiac cycle, so we weren't actually thinking about a normal human person, right? We could imagine that the heart is completely relaxed at the beginning of this process, and that there's a little bit of blood left over in the ventricles from the previous cardiac cycle, right? Obviously, we can't think about that in the patient because there's always blood flowing at any given time. But for simplicity's sake and to learn this for the first time, you can kind of imagine that the heart has nothing in it to begin with. So let's talk about how we can even draw this out. So this picture comes from your book, I believe, and you can start at the top, top 5th pi of it, and it's labeled as A. Here, can I zoom in? Right here. And this is where we'll begin with atrial systole. So here in this picture, and we'll talk about it in the picture first before we draw it out for ourselves, atrial systole, so this means that the atria are going to contract. And when the atria contract, they are going to eject a reasonable but relatively small amount of blood into the ventricles. And after it's done ejecting that into the ventricles, then it can relax, and all of that blood is going to be in the ventricles. And in order to maintain that blood staying in the ventricles, those AV valves are going to close. So now we have a buildup of fluid in the ventricles, and that buildup of fluid is going to increase the amount of pressure we have in the ventricles. And whenever we increase that amount of pressure, we're going to finalize that amount of pressure and exert one last contraction to finally push all of that fluid out. And so that's going to be ventricular systole. Once we finally contract those ventricles and push that fluid out through the the semilunar valves. At the same time, the atria are still relaxed, right? So they haven't yet opened their AV valves in order to receive blood. Then for a very, very short period of time, we can imagine the heart is completely relaxed and there's nothing in it, even though there's going to be a little bit of blood left over. And immediately after that blank period, the blood will continue to flow back into the atria to restart this entire process. And then the ventricles are relaxing during this time. And then last but not least, the ventricles, everything is immediately relaxed, and we're able to pour that last bit of fluid that we received in the atria into the ventricles, and we start the process all over again. So the way to read this graph, or this picture, is from the directions that we just showed you. And then also around the circle, you can notice that there's atrial systole in orange, and then atrial diastole in blue. And then outside of that circle, you have ventricular systole and ventricular diastole. So it's showing you what's happening between those two and where there's overlap. Okay, so let's kind of draw this out before we think about what is even really, like how we can manipulate this. So let's talk about the normal first. Okay, so I kind of like to draw this in 4 different sections. So I like the circular diagram, but it's a little confusing for me at first. So I want to draw it in in a linear fashion. So I would, if I were you, I would have 4 different chunks in your piece of paper. But since I don't have as much room, I'm going to do one at a time and go down. The first one I want to talk about is atrial. Let's actually let me draw it out first and then talk. So we have. Okay. So this is and the reason why I'm stalling, I apologize. The reason why I'm hesitating is because this is a cycle, and that means that you can kind of start anywhere in this process, and as long as you make it all the way through the process, it'll just repeat itself anyway, so it's kind of difficult to find like a starting point. So even though they say atrial systole here is the first starting point, I don't know, it's not totally my favorite, but I'll go ahead and do that here just to maintain consistency. So just imagine just before atrial systole what has to happen. So if this process is going to eventually be atrial systole, but what's happening right before atrial systole? So it's atrial, so we're talking about the atrium on both sides, and we're talking about systole, so that's contraction. So before we even contract the heart, we have to fill it with blood, right? So we're going to get some amount of blood filling into the atria on both sides. So there's going to be at least some amount of blood in the atria. And then we have atrial systole, which I'm going to draw stars to signify contraction. So then the atria contract, and all of that blood is going to shoot down into the ventricles. So the valves are nice and open here. Okay. After atrial systole, all that blood is going to be in the ventricles. And that blood will continue to take up the space in the ventricles. And remember that those valves are shut. So we don't have any backflow, we don't have any of that. We don't have any regurgitation into the atria, which is important. And after atrial systole, the atria are going to relax. So now they're relaxing. So atrial diastole. And at the same time, the ventricles are filling with blood. And after the ventricles fill with blood, then the ventricles will be ready to contract. So ventricular systole. And all of that blood in the ventricles, we will contract the ventricles, and all of that blood will shoot out to either the lungs or out to the systemic circuit via the aorta. And after ventricular systole, then we have to relax the ventricles. So we have ventricular diastole, where there's a little bit of blood remaining, not a lot. but the ventricles are starting to relax. At the same time as the ventricles are relaxing, we're still filling in with blood from the atria because they've been relaxing for a little bit of time now, so they're ready to receive more blood. So we receive some blood. And at the same time, these valves are going to be open a little bit so we can actually let all of that blood enter into the ventricles, and we're able to start the process all over again. So if I were to come here, I could draw this arrow back up here, and after we fill enough, or after we close off those valves and seal it shut, we fill the atria full with blood, then we open up those valves, have a contraction, close those valves, have the atria contract, fill the ventricles, build pressure in the ventricles, contract the ventricles, shoot that blood out, then the ventricles relax and you continue to fill with blood. And then this process just keeps going and going and going. Okay, so moving on. What happens to the time spent in each phase with an increase in heart rate? So what is heart rate, right? Heart rate is going to be the measure of how often the heart is actually contracting. So the amount of time spent within each phase during the cardiac cycle will decrease because we don't have enough time or we don't have as much of a luxury of waiting around for the blood to fill because we have to be ready for the next impulse and for the next contraction to happen. And because of that, that means we're probably not going to have enough time to actually fill the heart with blood as we normally would. And this concept, rewind the video if that doesn't make any sense, but this concept is going to be really important whenever we start talking about abnormal physiology and how we're able to actually control the normal physiology. So make sure that that component makes sense before watching the last video of this chapter. So how are we able to actually measure this and represent it somehow in the clinic? So that's going to be with an I have EEG here, and that should say ECG and EKG. And this is electrocardiogram, and this is also electrocardiogram, but the German spelling or something or whatever, like the Germans decided to use a K instead of a C. So, but they mean the same thing. And that's what's represented on the left-hand side. And this is actually coming from the section 2-1. I just think it fits in a little bit better here because we compare what's happening in the EKG with what the cardiac phases are. So the EKG has a specific shape to it. There's a first wave, then there's this like crazy mountain time, and then there's another wave, and then the thing repeats itself. And we have ways to identify the different parts of each of these pieces. And so we call this the PQRST intervals, where an interval is where P goes to Q and Q goes to R and R goes to S and S goes to T. But you could also think about it as, you could also talk about the PQRS interval. You could talk about the QRST interval. So anyway, from one point to another, that's an interval. And at each individual point, something specific is happening. So for the P wave, we have atrial depolarization. And this is where the atria are told, hey, the action potential has just begun, get ready to contract. So it's just that beginning piece. If we talk about this action potential, right, it's just this beginning piece right here. That's the P wave. And then we have the QRS complex. And the QRS complex is where we actually get the ventricles to contract. And after the ventricles contract, then everything needs to get repolarized so it can do it all over again. And so that time period is going to be called the T wave, or that green wave in there. So this is kind of a combination of what's happening in terms of charge and what that means anatomically, and then what does that mean like clinically for the patient at whatever time point. Okay, so then on the picture on the right, what I tried to do was take that previous picture that talks about the individual the conduction of the heart. So where we have the SA node talking to the AV node, and then the AV node talking to the ventricles, and when the contraction is happening. And I put it next to what's happening for the ECG. And at what point in time can you actually register where this electrical impulse is going? So for the first point, we're flatlined, we haven't started anything yet, and then the SA node is finally fired. And after the SA node is fired, it's telling the atria, hey, we're about to have a contraction, and contract. And then that signal finally gets to the AV node, and then the AV node travels or sends that signal down to the ventricles, and then the ventricles are finally told to contract. And then after the ventricles contract, then we have to have finally a relaxation period, which is not shown in this picture. That would be like step 6. So I talked about intervals. So segments is going to be so these would be segments and these would be intervals. So I'll put I here for intervals, and then these would be segments. And I have identified what happens at each individual interval. So from P to R, maybe I should draw this out here too so we have a reference. So P, Q, R, S, T. So from P to R, this is where the atria depolarize. So this is the beginning of the action potential, and we have just initiated a cardiac contraction. At the QT interval, this is where we start to do the repolarization. So from this is just telling you what, okay. So then from after R, so R to T is, just T is repolarization. So from this point over here is depolarization of either the atria and then the ventricles. And then the T wave is repolarization of both. Okay. And if there were any irregularities of this, and maybe perhaps an irregular heart rate or irregular heart rhythm, we would call that an arrhythmia. Something is not normal. So A for not, and rhythmic for being, or arrhythmia for being rhythmic. What might that look like? Well, we have other terms for it. So Brady means fast and tachy means slow. So bradycardia would be a faster interval of rhythms. Tachycardia would be slower. And the very bottom one, the top one is normal, and then the middle is bradycardia. So I said this backwards. Oh my goodness. I'm sorry. So the top one is normal. The middle one is slow. So bradycardia. And the last one is tachycardia, which is fast. If we had a pacemaker, we would be able to actually identify all of these points. If you take an advanced, coding, like a blue code, blue code, code blue for where there's a cardiac arrest in a hospital, then they actually ask you to learn the different types of EKGs and what that might mean for maybe what medications they were on or what they've been given or what next steps to take. And there's lots of complicated ways of being able to, or there's lots of complicated rhythms, and they might be a little difficult to interpret at first. So before even trying to tackle any of that, it's really important to understand just the basics of what's happening during that PQRST. So how can we actually measure, or how can we hear what's going on? We kind of talked about measuring, so now let's talk about hearing things with the stethoscope. Whenever we use the stethoscope, we're performing something called an auscultation. So you auscultate with a stethoscope. And whenever we are listening for heart sounds, we're listening for two specific sounds. There's a lub and there's a dub. And to be honest with you, whenever I listen to this, I don't really hear lub and I don't hear dub. I hear like two different tones of dub, but not really lub. But if that works for you, great. We will refer to it as lub and dub, but don't feel weird if it doesn't sound like lub and dub to you. If you do have a stethoscope at home, I strongly encourage you to play around with this and kind of have a faithful participant just sit there and let you do some sounds on them. Or perhaps if you work in a clinic, you might ask someone to show you how to auscultate on someone else. Because it is really interesting. If you do place the stethoscope in the positions that I have identified in the top right-hand picture, you can actually hear just individual valves on their own. So have fun with that. I highly encourage it. Okay, so what does lub and dub even mean? So lub is where the atrioventricular valves shut. The dub is when the semilunar valves shut. So we can't hear when they open, which makes sense because they would just be open and then there would be a whoosh of blood over them. There wouldn't be any like single sound to signify that they've been open. But we can hear when they shut because they slam shut almost immediately, and it's a very important step in the cardiac cycle in order for blood to continue moving in the way that it's supposed to. So that's why we focus on the shutting sounds. And so which one would you expect to hear first during a regular cardiac cycle? Should be lub, because if you remember, the blood comes into the atria and then goes into the ventricles, and then the ventricles shut, and that's going to be the lub sound. Then the ventricles are going to pass through the semilunar valves, and after they pass through the semilunar valves, those semilunar valves then shut. That's going to be the dub sound. And if for whatever reason there's like a whooshing sound, or it's not a consistent dun 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 dun, you might hear like a whoosh dun, or just a whoosh every now and then. That's what we call a heart murmur. And that typically means that something is malformed with some or all of the valves. And that might mean that they're not closing properly, so their adjoining structures aren't working properly. Or if it's ones that don't have supporting structures like the semilunar valves, then they might be misshapen or something else might be going on. Now let's talk about the pressure to volume relationship in the heart. So in this slide, we're going to talk about what we would anticipate this to look like. And then in the next slide, we're going to talk about what that actually looks like. And just to kind of orient you with what's going on in this picture, and we'll draw it out here on the right-hand side as well. So on the x-axis, we have time, and on the y-axis, we have pressure. So as we increase in y, we increase in pressure. As we increase in x, we're increasing in time. And down below are the heart sounds. So we can use the heart sounds to identify what part of the cardiac cycle we're in. So the lub sound should be when the AV valves close, and that dub sound should be when the semilunar valves close. So we should make sure that whatever we draw pairs well with those two. And we're going to talk about what the relationship looks like of all of the volumes in all of the chambers. And then we're going to simplify it and talk about just one chamber that's really the most important. So first of all, let's go ahead and draw a similar graph to the right. So pressure and time. Oh my goodness. Pressure, time, and here we're going to have lub and dub. Okay, so what would you say would the pressure look like in the atrium? So let's do orange, pressure in the atrium. So let's just think of the left atrium. Let's pick the left side. So the left atrium at lub, we can start at lub. Is the left atrium going to have a lot of blood in it or no blood in it during the lub sound? And the lub sound, remember, is when the AV valves close. So are we going to have a lot of blood in the atrium during this time or not a lot of blood? The answer should be not a lot of blood, because we just lost all that blood from the atria, moved into the ventricles, and the AV valve shut. So the pressure of blood in the atria should be relatively low. And then the valve shut. Okay, wahoo. And then dub. What's happening at dub? Dub is when the semilunar valves shut. So we're not even really talking about the atria at all during this point. So we can also continue this line down here. And we can continue across the way here until we start adding in some volume of blood. But as far as the pressure in the atria at any given time, doesn't really matter until we actually contract them. Okay, now what does pressure look like in the aorta? So let's think about the lub sound. Remember, this is the AV valves closing. The pressure in the aorta is probably also low because the AV valves are closing and we've just filled the ventricles with blood and they're continuing to fill. So the pressure here is also low. But what about at dub? This is when the semilunar valves are shut. So the pressure should be decreasing at some point, but the but the amount of blood, but the amount of pressure in the aorta was probably increasing at some point between these two, because blood was leaving the ventricles and traveling to the aorta, the left ventricle, and traveling to the aorta. So we should anticipate an increase in pressure because we shut the AV valves, then we contracted the ventricles, we moved blood out of the aorta, and then we closed the semilunar valves. So now the pressure should dip really quickly because the pressure in the aorta is going to decrease as the blood moves away from the aorta. And then this can continue on down like this. All right, what does the pressure look like in the ventricle? And let's stick with the left ventricle. So left ventricle. So what does the pressure look like in the left ventricle during the lub sound? So this is when the AV valves have slammed shut. So we've started to increase a little bit in pressure, right? And then when the whenever the AV valves close, then we immediately increase in pressure, lots of pressure, right? And at the dub sound, that's when we lose a lot of pressure because all of that blood has left the AV valve and has traveled past the semilunar valve. So then we should anticipate a decrease in pressure by the time we get to dub, and then we even out. Okay, now let's think about at what time points things are kind of happening at, right? So at these bottom two time points, we can mention that the first time point here, this is when the AV valves shut. AV valves close. On both sides. We can focus on just the left side if that makes it easier since we're talking about the aorta here. And then on dub, the dub sound is going to be when our semilunar valve shuts, but immediately after the semilunar valve shutting, the AV valves are also going to be opening. So right about here, we should think about the AV valves open, which means right before that, the semilunar valves shut. And before they shut, they have to be open at some point. So any time period between somewhere in here, right, we're going to have the semilunar valves open. Like they have to open before they shut, right? Okay, so now let's kind of all put this together and make what the graph actually is supposed to look like. This is just generally kind of what's happening as we change in time. So if you go to your next slide, you should have a blank slide in order to draw this out with me. And then on the next slide, we can talk about what's actually happening. So here, looks like we got a lot of things right. We kind of got the general shape right. Looks like there's a lot of space here in the middle, which is good. Looks like we got the valves opening and closing correctly. We were talking about the pressure in the atrium being relatively low, which we got right. The ventricle pressure also changing pretty drastically at some point. And then the pressure in the aorta, we got a little bit wrong, but that's okay. We still got a pretty steep curve at some point, which makes sense. And the pressure in the aorta is always going to be a little greater than the pressure in the atrium, which makes sense because the aorta just is going to be facilitating a lot more pressurized blood flow than the atria would be. So that's why we would increase that aorta pressure. So what does this curve even represent? Like what, why do I need to know this? So let's draw a simplified version of this curve. Okay, so remember this is time, this is pressure, and we can combine all of these curves into one curve. So, and I'm going to make it super, super simple. Boom, 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 and boom. And if you wanted to connect the dots, sure, you can connect the dots. Because this is cyclic anyway, so this is all going to happen all over again. So we can bring this back this way, and we can go boom, 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 boom. You're right, we can do this over and over again, right? Okay. Okay, so it's important to know a couple points and what's happening during these time points, which I'll label in orange. First, it's important to understand what's happening at the points when things start changing, right? So at some point, we increase a bunch of pressure, which means we probably are closing off something. So I would fill this in, right? And that corresponds with the graph on the left, right? The AV valves AV, close. And we can be more specific about the left side, since the left side is what is pushing against the systemic pressure of the body, and the left ventricle is the one that has the thicker amount of muscle, and that's the one that we really care about. The right ventricle is nice, but it really just kind of goes to the lungs and whatever, woohoo, great, but the left ventricle is really what we care about, so we're just primarily concerned with left side stuff. Okay, so AV valves close, which means at some point they have to open. And if they were at really high pressure down here, if they were at a really low pressure here when they were closed, then we would expect their pressure to, again, drop off whenever they're open so that they can stay at a relatively low pressure. So here we're going to say AV valves are open. Then we have to talk about the semilunar valves. And the semilunar valves, whenever they are closed, means that there's not going to be any pressure in that area because there's no blood flow. They close, there's nothing going on in there. So that's going to be catty corner to the other one. And this is specifically the aortic semilunar valve. And then that means that this is going to be the open one. Semilunar valve, close. Oh goodness, close. Open. Okay. Let's just make sure that this makes sense, right? So the AV valve closes, okay? That means we're going to increase in pressure because there's a bunch of blood in that area and it's going to create a big amount of pressure. Okay, great. Then the semilunar valve opens so that all of that blood can escape and leave the ventricle past the semilunar valve into the aorta. And as we do that, we're going to have an initial increase of blood pressure because it shoots out of the aorta, but then it kind of dips back down. And then finally the semilunar valve closes, which means there's no blood in that area, so we basically drop almost down to 0 in pressure, and the AV valve opens so we can do this all over again. Fill with blood, close it, increase pressure, so on and so forth. So there's some other things that we can identify in this graph. This representation and these values are not arbitrary. There's a lot that we can actually measure with this. So for instance, when the semilunar valve opens, this period of time is when blood leaves the aorta. And when blood is leaving the aorta, we actually call this ejection fraction. And I'll tell you what it's a fraction of here in a second. But it's being ejected out of the aorta. And so we would expect a slight increase at the beginning, right? Slight increase in the beginning, and then eventually tails down for pressure. Okay, that's number one. Number two, we can think about the differences in Y and the differences in X, right? So we talked about how the difference in X is going to be time, right? So over time, this is one cycle, yeah? And then we can talk about the differences in pressure. So we go from a small amount of pressure because there's some amount of blood left in the ventricles at any given time, and then we go to a really, really high pressure at some point. So what does this actually mean? What does this space actually mean? Well, this is the amount of blood that's actually moving during any given contraction. And the amount of blood that's moving during a single contraction is what we call stroke volume. And the ejection fraction is going to be what fraction of the amount of blood from the stroke volume was ejected out. So that's what the fraction is coming from. So stroke volume is the amount of blood in the heart that moves during one how do we say this? One left-sided contraction. Okay. All right. So the width, actually, we can use to determine what that stroke volume is, and I abbreviate stroke volume as SV. Ejection fraction can be abbreviated EF. And what else? Okay, I think that's it for now. Okay, so your book actually does oh, there's one other thing I need to point out. There's one other thing I need to point out. So in blue, let's do a purple. So we can also measure how, or we can also change where this graph is, right? So if we were to take the same graph and let's just make like a normal looking, so let's just say that this is the normal. This is the normal, right? So stroke volume equals whatever that distance is, right? Ejection fraction equals whatever that is, okay? The amount of pressure it takes to open the, or to shut the AV valves is there. The amount of pressure that is within the ventricle at any given time, that's always going to be residual, is there. And then we can always move this graph somewhere else, right? Like it doesn't always have to be here. This is just kind of an average of where it would fall for any given person. But if we were to change how good the heart was at moving this blood, we can change a couple things. We can change the time in between the valves opening and closing. So we can change the distance across X. We can also change the amount of pressure that is able to be built up within the ventricles by changing Y. So let's imagine a heart failure patient where that muscle is no longer as thick as it used to be, and it's pretty floppy, and it's not very good at holding on to the blood and being able to produce enough of a contraction to push it out. So maybe we'll have a lot more or a lot less blood to work with, depending on what the situation is. So how do we measure? One other thing that we need to measure is how good is the heart at actually pumping and moving stuff out. And in order to really determine that, the way you can really measure it is by the amount of blood that's leaving at any given time. And not at any given time, but during each contraction. And in order to measure that, we can think about the beginning of the ejection fraction, because that's going to be the point in time at which the most amount of pressure is going to be built, and that could represent the amount of force that the heart was able to produce in order to move that amount of blood. So what time point would that be out of our 4 dots here? Well, it would be this time point. And if we wanted to measure the slope at this time point, and we could measure the change in slope if it was decreasing or if it was increasing, and then that slope is actually what is our contractility, or the ability of the heart to actually make a contraction, right? Like if it's a forceful contraction, we're going to increase contractility. And if we increase contractility, then we're going to increase pressure. If we don't have enough contractility, we're going to decrease pressure, which means that the line is going to be more level, which means we're going to decrease the amount of pressure. Okay. So anyway, so some additional things to think about, and this will definitely get brought up in the next video, but just a kind of an introduction here and how it relates. Okay, so your book gives you a really nice summary picture of what's going on for all of this that we just talked about. And it lays it out steps 1 through 8 about what's going on, and this is all going to include everything that we already talked about. But what I like about this picture is above it, it also tells you exactly what's happening in terms of the EKG and the cardiac cycle and where that pairs along the way. So if I wouldn't start with this image all at once unless it really makes sense to you. I would really think about these in pieces and then put them all together. But if this image makes sense to you and you want to break it down from there, great, enjoy. But just know that we don't care too much about the volume piece that's down here in the bottom image, where it says like 1, 2, 3, and it shows you stroke volume, end diastolic volume, and systolic volume. We have a better way of representing stroke volume, which is what I showed you here. So just keep that in mind. I do like this picture. I think it does a good job of explaining what's going on. So what I did was I paired it with the previous picture in your lectures so that you could actually see visually what's happening in the heart. And these steps are again laid out here in the very top piece here with the EKG. And then I worded out what's happening, or I explained in words what's happening for the last part that isn't included in the EKG. So what happens after step 5? I've worded it out over here. So hopefully this is helpful for you whenever you go back through your notes and learn the material. Okay, so now we've gone through the cardiac anatomy, which is really important before we went through the cardiac physiology. And now that we've learned both of those, now we can talk about how normal what factors contribute to the normal cardiac physiology and how we can change that if we need to. And so I'll see you in the next video for that.